we can analyze quantization error and the effects of it, and recall that when we do quantization, we're rounding the input signal, say x of n, we're rounding that to the nearest multiple of capital delta. And if there was no quantization, then the relationship between the input and the output would be a straight line. But we have this stair step, which is associated with the rounding process. Now what we know so far is that if I define the error as the difference between the true value and the quantized value, that error is between minus delta over 2 and plus delta over 2. Now we'd like to understand it a little bit better, and I can give you an example here where I took a cosine and I quantized it with 33 levels. So what you have here in the top panel is a quantized cosine, and you can see that it gets stuck here at 1 near the top, and then it drops down and takes some uneven steps, and that occurs throughout the range here. Well, if I look at the error between the true cosine and this quantized value, I get something that looks like this down here in the bottom panel. And even in a simple signal like this cosine, these errors appear to be pretty complicated. Okay, some of them are small, some are big. Sometimes one's big, then positive. The next time one's big, negative, or sometimes you get two that are close together, both small. And there's a pattern in this, even for a very simple signal like a cosine, is quite complicated. So in general, as far as understanding this, we'd say it's kind of unpredictable. And therefore, we're going to use a statistical characterization to account for the randomness that we observe. Before we look in detail at the characterization of quantization error, we need to introduce a few terms for those of you that are not familiar with probability and random processes. So first term that we're going to look at, and it's going to play a role here, is the term stationary. And stationary plays the analog in random signals of time invariance does with systems. Because when we say that a process or a random signal is stationary, what we mean is that the statistical properties of that signal don't change with time. If I look at time 1, I'm going to have basically the same statistical characterization as I do at time 100. Now, a random process, that term is used to describe a model for a signal with uncertain characteristics. So if the signal has uncertain characteristics, in other words, we're not sure what signal we're going to get, but it behaves in a way that can be characterized by the laws of probability, we call that characterization a random process. Now, probability distribution describes how likely it is that we observe different possible values of a random quantity. And I think most everyone's familiar with a bell curve or a Gaussian distribution, which says that most of the time you're going to get values that are in the center of the curve, and relatively rare or unusual to get values that are outside the center of the curve. And we say that a signal is uncorrelated if the values of the signal at any two times appear to be unrelated. So if, let's say, I look at values of the signal that are, say, 10 steps apart. Well, if no matter where I look in the signal, the values that are 10 steps apart appear to be unrelated, then I'd say it's uncorrelated. Now, it might happen that if I look at values of the signal 10 steps apart, I see that whenever one's positive, the one 10 steps later is negative, and vice versa. In that case, the signal would have correlation. And then finally, we have the idea of independence. In simple terms, we say that signals are independent if there's no relationship or pattern of any sort that links the signals or links the random quantities. So those are terms that are going to come up when we characterize quantization noise. Now, our model for quantization error is that the input goes into a quantizer and produces this rounded signal that's quantized xq. We can think about that as taking the true signal x of n, adding an error term to it to get the quantized signal. And in this characterization, the error term has certain properties. First of all, it's typical to model the error term as an observation of a stationary random process. That means that the characteristics of the error aren't going to change over time. Secondly, we saw initially that the quantization error had to be between minus delta over 2 and delta over 2, but it's common then to assume that it's uniformly distributed between those extremes. In other words, it's equally likely that the quantization error could take any value between minus delta over 2 and plus delta over 2. That gives us a probability density function that has amplitude 1 over 2 and is constant everywhere in here. So it says all values in this range are equally likely. Third, that the values in the quantization error sequence are uncorrelated with one another, that they don't appear to be linked. And then finally, the fourth assumption that's usually made when modeling quantization error is that the error is independent of the signal x of n that we started with. Okay, that they're not linked in any way. Now, of course, they are linked because x of n is how we got EQ, but that there appears to be independence between the two. You don't see an obvious pattern. And if we go back to my example of the cosine, at first glance, even though this is a very simple signal, there doesn't appear to be an obvious pattern that links the values of the cosine to the values of the error. Now, these assumptions, it turns out that they're reasonable if the quantization interval delta is sufficiently small so that x of n jumps over several levels between samples, and if x of n appears random. So the sinusoid actually violates these assumptions, and if we looked at the statistics, if we characterize the quantization error, we'd find that it's correlated in the case of the sinusoid that I've shown you earlier. But for more complicated signals that are, apparently random, like speech or music or things like that, then it turns out these four properties of this model are pretty reasonable, provided we have small quantization intervals. So with these properties, we can talk about something called the signal to quantization noise ratio. In other words, how big is that error term? It's common to define this in dB, so we'd have the signal to quantization noise ratio, SQNR, 10 log 10 of the ratio of the power in the signal, x, to the power in the noise. And so this tells us how much bigger the signal is on average relative to the noise. Technically, sigma x squared is the variance of the signal, and we're going to call that power, and sigma e squared is the variance of the error term, which we can actually compute using our model for the probability distribution. So here I've added in the definitions of the variance or power in the signal x of n and in the error term, and this is the expectation operation, and you just should think about that. If you haven't taken a class in probability and random processes yet, you should think about the expectation as an averaging. So on average, how big is x squared of n? On average, how big is e squared of n? Now it turns out that the variance is defined in terms of the probability density function. You basically integrate the square of the value against the probability distribution. And if we do that for the uniform probability distribution associated with the quantization noise model, we have that we're integrating minus delta over 2 to delta over 2 of 1 over delta times e squared. And that comes out to be e cubed over 3 delta evaluated at the limits of integration, which gives us delta squared over 12. So the power in the quantization noise, if it's uniformly distributed as we are modeling it, is the quantization interval squared divided by 12. Therefore, substituting for sigma e squared, we find our signal to quantization noise ratio is 10 log 10 of 12 sigma x squared divided by delta squared. We can express the signal to quantization noise ratio in terms of the number of bits that we're going to use and the range of the analog to digital converter as shown here, because the quantization interval or step size is given by the range of the analog to digital converter divided by the total number of levels. Since we're using b plus 1 bits, we have 2 to the b plus 1 levels, and R represents the difference between the maximum value we want to represent and the minimum value we want to represent. So substituting for delta, we have that the signal to quantization noise ratio can be expressed as 10 log 10, 12 sigma x squared, and then we'll have 2 to the b plus 1 quantity squared divided by R squared. We can use the properties of a logarithm. The log of a product is the sum of the logs, as well as the log of a number raised to a power is that power times the log, to rewrite this in a more convenient form. In particular, if we take 10 log 10 2 to the 2b and pull the 2b power out front, we end up with 20b times log 10 of 2. We have 20 log 10 of 2 for the 2 to the first power here, and then 10 log 10 of 12, and finally minus 20 log 10 of R divided by sigma x. Now here sigma x is the square root of the power. We can think of that more like a standard deviation. And we have to make some assumptions about the relationship between the maximum and minimum values of the signal that we want to represent and the standard deviation of the signal. And one reasonable assumption is to assume that we're going to allow the signal to vary between plus or minus 4 standard deviations. In other words, the maximum value we're going to be willing to represent is plus 4 standard deviations, and the minimum value is minus 4 standard deviations. And if we do that, then R becomes 4 sigma x minus 4 sigma x, or 8 sigma x, and this ratio becomes R over sigma x becomes 8. And taking the various logarithms of the constants involved, we end up with the signal quantization noise ratio of approximately 6.02b minus 1.25. And the 6.02b comes from this first term here, because 20 log 10 of 2 ends up being 6.02. And then the minus 1.25 are the rest of the constant terms. So we see that every bit gives us an additional 6 dB of signal to quantization noise. And this formula can be used to gauge how many bits are needed to achieve a specific signal to quantization noise ratio. For example, suppose we want to have a 40 dB signal to quantization noise ratio. If we solve for b, we find that, and restrict b to be an integer, we find that we need b equals 7. And since the number of bits was b plus 1, that implies that 8 bits are required to get a signal to quantization noise ratio of 40 dB if we're assuming that our range of our analog to digital converter is plus or minus 4 standard deviations. Well, we're going to conclude this with just some observations about what this kind of model means if we're going to be filtering. Here we're showing our ideal signal x of n, and then the error term that gets added in to produce my quantized signal. So when I put my quantized signal through this filter, I can think about that as if I had the output due to the true input x of n plus an output error term, which corresponds to taking the quantization noise and running it through the filter. So the characteristics of the noise at the output of a filter are going to depend on the filter itself, because the filter gets applied to the quantization noise. Now, there's one other set of comments I should make here, and that we're not talking about at this point is the effects of rounding in the computation. When I implement this filter, I'm going to have, let's say I have a b-bit number coming in, and my filter coefficients are stored as b-bit numbers. Well, when I multiply those two b-bit numbers, I get a number that needs 2b bits to be represented. Therefore, when I round that back down to b bits, I'm throwing away some information, or I'm introducing a computational noise. due to rounding in the arithmetic. Now, if you're using floating point arithmetic, that's not such a problem, but if you're dealing with a real-time application where high speed is essential, then fixed point arithmetic, you have to worry about those kind of effects as well, and those create yet another source of error that contaminates the output of the filter. But that's an advanced topic for another time.